Welcome to Học tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, a history of science in 100 experiments, today we will read story number 67, Light from the Darkness. The famous test of Albert Einstein's general theory of relativity, carried out during observations of a solar eclipse in 1919, is a classic example of the scientific method at work. A new idea, in this case the general theory, makes a prediction, which is tested by experiment. It passes the test and becomes established as a good scientific theory. Before Einstein came along, the best theory of how the universe worked was based on Isaac Newton's law of motion. These describe the way things move in an unchanging backdrop of space as time passes, with time ticking away at a steady rate like some great universal clock. Einstein's general theory of relativity, which he completed at the end of 1915, was also a description of how things move in the universe, but in his theory, the rate at which clocks tick depends on how fast they are moving, and space itself is curved by the presence of matter. Among other things, this means that light from a distant star passing close by the surface of the sun would be deflected by a tiny angle, because of the way the mass of the sun bends space. Einstein was well aware of this and used his theory to calculate the size of this deflection. As it happens, Newton's theory also predicts that light will be deflected as it passes by the sun because of the gravitational influence of the sun on what Newton thought of as particles of light. But crucially, the size of the deflection predicted by Einstein's theory is exactly twice as large as the deflection predicted by Newton's theory. The effect predicted by Einstein was a deflection of 1.75 seconds of arc. Newton's theory predicts 0.875 arc seconds. Here was a clear-cut way to see which theory provided a better description of the universe. If only there was a way to look at stars almost directly behind our sun. The way to do this, of course, is to photograph the stars when the light of the sun itself is blotted out by the moon during a solar eclipse, and compare the prints with photographs of the same part of the sky taken when the sun is not in the way. Einstein knew this, but with the First World War raging in Europe, he was in no position to arrange for observers to make the test. News of Einstein's ideas traveled quickly to scientists in neutral Holland, and from them to astronomers in England. There, Arthur Eddington realized that a suitable eclipse would be visible from the island of Principe, off the west coast of Africa in 1919. He obtained permission to organize an expedition to test Einstein's theory, provided that the fighting in Europe stopped in time. When the armistice was declared in November 1918, even though Britain was still technically at war, the peace treaty was not signed until June 1919. He was given a go-ahead and just had time to make the arrangements. He was able to obtain the crucial photographs on May 29, 1919, even though the observations were hampered by cloud. They were just good enough for his purpose. When the photographic plates were compared with photographs of the same part of the sky when the sun was not in the line of sight, they showed exactly the amount of deflection predicted by Einstein, twice as much as predicted by Newtonian theory. Newton's theory is still good for many things, such as calculating the fall of an apple from a tree or even the orbit of a spaceship on its way to Mars. But it is not as good as Einstein's theory at describing the universe at large. Eddington announced his results to a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919, just 4 years after Einstein had presented his general theory to scientists in Berlin. Since then, the general theory had passed many other tests and is still regarded as the best theory of time, space, and the universe that we have. The light bending effect itself is now seen on a very large scale, where the whole galaxies of stars and even clusters act as gravitational lenses to focus the light from even more distant objects and make them visible to our telescopes. There is also a more practical application to the general theory. The instruments used by GPS satellites to work out the position of objects on Earth are so precise that as they move in the Earth's gravitational field, they have to take account of the effects described by the general theory. Every time you use sat-nav or find location facilities on the smartphone you are using and, in a sense, testing the general theory of relativity. To the vocabulary section, general theory of relativity, general theory of relativity, prediction, motion, backdrop, presence, description, blotted out, raging, permission, expedition, armistice, technically, orbit, spaceship, gravitational lenses, satellites, precise, precision. There are so many tongue twisters in these stories. This story is hard to read. Anyway, thank you very much for your time. And as usual, I will see you in the next story. Bye for now.